then my n will be 2, because it is saying that it has 2 into n integers for sure. Now we need to partition nums into two arrays of length n. So nums is this array. We have to partition this nums into two length n arrays to minimize the absolute difference of the sum of the arrays. And my partition operations should be such that the difference between the sum of the two n size arrays formed out of this 2n array should be as minimum as possible. Now to partition nums, put each element of nums into one of these two arrays. And now to make these two arrays, because we know that we have a 2n size array, to make a n size array, I will partition this. Now when he's saying to partition this, which means one partition will have n elements, other will have n elements. So the first partition, which means n elements, you can just put any of those n elements. I can put this element of this and this element in the first partition. The partition can have any element. So you can just imagine that one partition will be a subset of size n of this specific array, and the remaining element will go in the other partition. Okay, super great. So very obvious that we can simply see that, okay, we have n elements. Great, we have these n elements, and I know one thing, that I need the firstly I will have to make a subset. Again, this is a big N. If you remember in our problem, this is a big N. Big N is the size, actual input size, but I will represent by 2 into small n. So whenever now I'll refer as small n, you will say, okay, small n is nothing but the actual partition size, right? Okay, great. So I have my big N, which means big N elements. Now for sure I know one thing, that I will have to get a partition of n elements, but that partition of n elements, it should ideally, I should try for all the subsets, which means for this I will try all the subsets, and for that specific subset I will have to go and get the sum. Okay, so one thing I have known, one thing I can think of is that I can try, because again I want one partition having n elements and then I want its sum. So I know I can make n, like I can make, it's a subset sum problem, that I have to grab n elements, and that n elements will just be the subsets forming a subsets, and then get the sum out of it, and the same goes for the other n element and get the sum out of it. So one thing is for sure, if I just simply say a simple algebraic expression that my sum1 plus sum2 should be equal to the entire total which I have, right? So for sure my sum2 will be nothing but my total minus sum1, and thus the difference which I should be having of two partitions, which means sum2 minus sum1, it is what I wanted in the answer. So I can simply say it will be nothing but my total minus 2 into sum1. So which means for sure that if this thing is more than equal to 0, then I can easily say that my total is more than equal to my 2 into sum1, or my sum1 is less than equal to my total by 2, or ultimately trying to say that my sum1 ideally should be as close to total by 2 as possible. Aryan, but why? Because if let's say your sum1 is exactly total by 2, if your sum1 is total by 2, now you know one thing, that your entire summation of the array, this array is total, so for sure the remaining one will also be total by 2, so the difference will be a 0, which is as minimum as possible. So it is a reason I would always want my sum1 to be as close to total by 2 as possible. Okay, great. Thus one thing we have seen, that I will try my sum1, which is, okay, the partition which was of big N size, I will take n elements. But Aryan, why you did not try for all the partitions? And then, okay, if I try for all the partitions of this big N size, then it will be whole raised by big N. But I can reduce this complexity by using only the n elements. So I'll just take n elements, and I'll simply make the partition out of it, which means I'll take the n elements and I'll take the subset out of it. So no worries, like we'll see that how actually we are trying to do it. But now we saw that we will simply take and want my sum1, which is nothing but n elements subset, and again there can be 2 raised power n subsets for n size elements, and for that the sum should be as close to total by 2 as possible. Now, and whatsoever is the closest possible value, I will take that. So I could see, okay, my subset sum should be equal to, now it's not exactly equal, but it should be equal to my target. It is relating to that kind of problem, which is subset sum problem, which is a very standard problem. In that problem, it says that you have n elements and you want to achieve this target sum. Just tell me if it is possible or not. That is the subset sum problem. But in my problem, I am saying that maybe it is not possible to achieve my target. Again, remember, maksad or target is total by 2. Maybe it is not possible to achieve this value, but this last line of my DP, if you remember that if you build this problem, subset sum, again, it is not used in this problem, but it's just for reference that usually it's a very standard problem to find the subset sum and matching that with target. So if you had known it, like if you had known it, so you might connect with that. If not, then you can simply listen this. For sure in future you will hear this problem. Now in this, when we build the bottom up approach, we see that in the last row I have, okay, considering I have n elements, can I achieve a target of 0? Can I achieve a target of 1? Can I achieve a target of 2? Can I achieve a target of target sum? This is my last row represent, right? Okay, great. So which means, okay, taking n elements and achieving that specific target, either a 0, 1, 2 or the target value. So I'll say that, okay, I'll simply use this last array for someone. For my someone, what's the best possible value he can get, and thus trying to minimize my target minus 2 into someone value. Because if you remembered, my difference between my sum 2 minus sum 1 will be nothing but my total, which is this entire total sum, minus 2 into my sum 1. So I will just try to minimize my this total minus 2 into my sum 1, and this I have achieved in from building my this bottom up array. This represents the target sum and this represents the n elements. Now if we go and try to use this, we know for sure the time complexity of this approach is time is n into sum, which is the possible sum. As you can see that if my sum is 10, so I'm trying for 0, 1, 2, 3 up till 10 as sum, and this is the n elements. So for sure my complexity will be n into sum, and the space will also be the same. But if you have learned this problem, so there's an optimization also, which is O of sum optimization, which we can have. But still, if we go back and look at our constraints, our sum can be very large, our sum can be 128. Because you can see number of elements are itself 127, like the maximum value of element is 127, and I can for sure have 10 elements. So for sure at least my sum can go to 128, right? And sum into n then for sure can go very long, but this 128 will itself not work in both space and time. So for sure one thing is, I am very sure my DP solution will never work. Thus now one thing is out of the picture. DP solution is actually pretty complex, like it's very large in time complexity. Now let's learn a new concept called as meet in the middle. So in this problem, again, I'll start off with a very basic problem in meet in the middle, and then we'll go on to the actual implementation which is used in the above question. So this problem says, meet in the middle says that we are given an array of n numbers, right? As he showed above that you also had n, big N numbers, and in how many ways you can choose a subset of numbers with the sum as x. Now I want to choose the subset of numbers. Again, I have n numbers in total. I have to choose a subset of them such that with the sum is x, such that the sum is x. So as you can see in this problem, I have 4 elements, 1, 2, 3, 2, and my subset, which the sum which I want to achieve, x, is 5. So I am saying how many such subsets are there. So one very obvious brute force way is just go and try to build all the subsets. So what I will do is I'll try to build all the subsets. Now building all the subsets of size n is nothing but 2 raised to power n. How we say we build a subset? Take, not take. For the first element I have two options, either I will take it or not take it, take it or not take it, take it or not take it, take it or not take it. So that is how I can build my subsets, and number of subsets built will be 2 raised to power n. Okay, great. Now when they are built, I have to then go and have a quick check that if their sum is actually equal to my 5. If yes, then it is the answer. So for this question, the answer is 3. As you can see, you can build 3 subsets. The first subset is 1, 2 and 2. because the sum is 5. Next subset is 2 and 3. The sum is 5. Next subset is 3 and 2. The sum is still a 5. But Aryan, 3 and 2 and 2 and 3 both are same. No, because this 2 is different and this 2 is different. So 2 and 3 is one subset, and this 2 and this 3 is one subset. So that's the reason I have in total 3 subsets whose sum will be equal to my value, which is x, which is a target for me, x. So now you remembered the time complexity of this to build all the possible subsets will be nothing but 2 raised power n, because I have 2 raised power n number of subsets. Now it is not the problem where it ends. You have to go and also find the sum for each subset, which will again take a O of n time, because the size of a subset can at max be O of n. And then we have to check if its sum, the sum which we have found in the previous step, if its sum is equal to my O of n. If that's the case, it's an O of 1 time, okay, just an equal operation. So you saw, to generate all the subsets, I am taking 2 raised power n time. To just find the sum of that specific subset, I'll take O of n time, and then to compare that with my target, which is x, I'll take O of 1 time. So my total my total time which I will take is 2 raised power n into 1, which is n into 2 raised power n. Now, if I see the problem constraints, my n was a 40. So 40 into 2 raised power 40 will never work. So, because see, this value is very high. The maximum 2 raised power value which can actually work is a 2 raised power 28, which is 2 into 1 is 7, around that. So for sure, I can never go this high value. Now, what is the solution of this? The solution is you don't have to try for the entire array of length n. Why? Rather, try for half a length. But half a length will not solve the problem. It will solve because if we go on and ask him, bro, rather than trying for the entire length of 40, you do one thing. You bifurcate the length into 20 and 20, and then just go and produce all the subsets of the length 20. Go and produce all the subsets of the length 20. So this was my input array of length n. I just did one thing. I bifurcated that length to half length, and then this half length I went on and asked, bro, please generate all the subsets of this half length, which is n by 2, which means for us case it is 20 length. So you will see I generate all the subsets, which means 2 is for 20 subsets for my half length. Again, I'm just taking the worst case. This 20 is the worst case, not for this. It is a 2 for this case, but I'm taking the worst case possible. And same way, I'll generate all the subsets for the right half length, which is again 2 is for 20. Now, when this left and right both are done, which means I've generated all the subsets for the left part, all the subsets of the right part. I will now go and check what? See, I generated all the subsets in the left part. As you can see, one can be empty, one can be only having one element, which is 1, only having one element, which is 2, and other having both the elements. And the same way, empty, 3, 2, and 3, 2. Now, if you remembered, I want to have a sum as my 5. So if I am saying I am taking my sum as 0, so ultimately I am also saying that, okay, in the right portion, I should be able to find the difference, which is target minus this sum 1. So I will try to search for a value of 5 in the right portion. So I'll just say, yeah, 5 I can find. 5 I can find, voila, great. You have find one subset which has 0 element from the left portion and 2 elements from the right portion, and that's how you can get the target sum. Okay, we will try for this next value. Now, if I have got a 1, remaining value which I have to find is 4. So I'll try to search for a 4. Now searching for a 4 in this portion. Okay, so 4 is not there. So okay, simply skip. Go on to next. Here the sum is 2. I'll try to search for a difference which is target 5 minus 2, because 2 I've already got. So I'll search for a 3. 3, 3, 3. Yeah, I can search a 3 here. Yeah, 3 is there. Okay, one subset you have again found. Okay, currently you have the value as 3. You will go and try to search for a value of 2. Okay, you have got found the value of 2. So that's how you can see that I have achieved 3 possible subsets. But the best part is this, for the searching part, you don't have to go and linearly search the entire subset. Nah, I can simply keep track it in a ordered, like unordered map, that okay, this sum I have, this sum I have, this sum I have, and this sum I have. If I have this sum, which means for sure I will be able to make a subset out of it. And that's how by using simply an unordered map, you can keep track of the elements which I can achieve from the right portion. And thus you saw I will only have to iterate on my 2 raised to power 20 elements individually, 2 raised to power 20 elements individually on the right part to make these simple maps and their corresponding sums. When they are built, I'll again go on the left part, and for the corresponding left part again I will remember my maqsad, my aim, my maqsad will be to search for the remaining difference in the right part, because only the right part can bring me that difference value. If he cannot bring, okay, it is not even possible, but if he can bring, just take that specific value. And thus I will simply be taking 2 raised to power 20, my 2 raised to power 20 again. This is a plus because individually I'm going on to both of them, and then ultimately I go on the 2 raised to power 20 again, but that's again a plus. And with that, in O of one time, I can simply go and check on the right part that if I have that sum or not in the right part. If I have that sum, which means if I have a value of 2, the remaining difference got is a 3. If I have a 3 in the right part, great. Simply go on. If I don't, then try for the next subset sum. And that's how you reduce your complexity from 2 raised to power 40, 2 raised to power 40 to 2 raised to power 20. And that's a very significant improvement, and this is called as meet in the middle, which means that you had a big problem. You knew that you cannot generate all the possible subsets, just thus you divided that and generated half of the subsets and used those half of the subsets to find the answer for the other half. Again, half on the left, half on the right, and thus you can simply get the answer. Now coming on, again you have got the implementation and how is actually the intuition of my meet in the middle problem. Now come on to the actual problem, which was that I am given an array of nums. Again, remember I have 2 into n elements, so I'll represent my big N by saying I have 6 elements, but then my small n will say I have 3 elements, which means my one array will have 3 elements, other array will have 3 elements. Okay, great. Now I need to partition my nums into 2 arrays of length n to minimize the absolute difference of the sum of the arrays. That is the question which we have already seen. So I knew one thing, that I cannot try for all the possibilities, because if you remembered, my big N, which is the entire size, this big N will be a 30. I cannot try to generate all the subsets of this big N length, which means 2 raised to power 30 I cannot do. So one thing I got to know, that I cannot do a 2 raised to power 30, so I'll divide that, which means I will try to generate my 2 raised to power 15 and 2 raised to power 15, which means I'll generate the subsets for the left part and for the right part, and from that I'll try to build my answer, because I know something of meet in the middle sort, meet in the middle algorithm kind of thing can be applied to this problem also. So now, okay, now I'll just simply say that, bro, you have this n as 6, divide that to left and right, and then generate all the subsets of left and right individually. So I know I have my left, in the left portion I have 3 elements, right portion I also have 3 elements. So I'll generate my 8 subsets on the left, I'll generate my 8 subsets on the right. Let's see how those subsets will be generated and what I will actually build out of those subsets. Because if you remembered above, here I just simply did one thing. I just simply took the sum of the, okay, I just simply took, okay, I have the element, so the sum of this specific group is 3. So I'll just simply go and try to find a 2 on the right portion. But here what else, obviously what extra I have to do, let's see that part. So firstly, I'll generate all these subsets. Now usually you will see, okay, empty subset, a subset of size 1, a subset of size 2, a subset of size 3. Okay, this is on the left portion, which means I generated 8 subsets, and the same way on the right portion I generate my 8 subsets. Okay, when this is done, there's one thing which you remembered that I have to do. I have to take the sum. I have to take the sum of that specific subset, which means, okay, I will have this entire array of length big N. I'll divide that and make an array of length small n, but the small n length I want to have the sum of that elements. So one thing I am pretty sure of, that I will need to have the sum of that n elements. So I will know one thing, that okay, for this from this left portion, okay, for size 1, what all sums are possible? I can have a sum of 0 or a -1 or a 2. So I'll just keep track of this entire thing, and that will be useful for us very much. Let's see. So I will just make sure, okay, in the left portion for a size of 0, I can have what all possibilities of sum. I can have only one sum, which is a 0, because empty is nothing but a 0 sum. For a left, when I have one element from the left, again, I just took this left. Now, even in this left, if I take only one element, again, when I say only one element, I will ultimately go and say in future that remaining two elements for the because if you remembered this entire array of big N size, I will divide this into the small n elements and small n elements for the final answer. Now this part 1, let's name it as part 1, and this is the part 2. Again, this part 1 is built out of the subsets, which means this part 1 can be, let's say, 2, -2 and -9. This part 1 can be anything. This, I'm not saying this as a part 1, I'm saying this part 1 can be anything, and I just want ultimately for me I would just want to have a partition. This left and this right, its difference should actually be minimum. So imagine this part 1. Now this part 1 is nothing but built out of this left subset and this right subset, because you can see left subset, if I just see this part 1, this part 1 is containing one element from the left subsets and two elements from the right subsets, right? That's the reason I'm ultimately keeping track of both the size and the sum. So for one element, if I take one element from the left portion, I will have the possibilities of sum as 0, -1 and 2. 0, -1 and 2. For the size of 2, I can have a possibility of sum as -1 or 1 and a 2, -1, 1 and a 2. For a possibility of sum as a 3, I can have only one possibility, which is nothing but a 1. So these are possibilities. This is a size and this is the possibilities of sum for that specific size. And the same way I'll make for the right also. For right, for a size of 0, my possibility of sum is 0. For right, for a size of 1, my possibility of sum is -9, -2, 4. And that's how I build my left and right, because I know I will be using that for my part 1 and part 2, because part 1 can be built by partial left and partial right. That is the prime reason for me to keep track, okay, because I know part 1 size can be n. So from left, if I take a number of elements, so from the right I will have to take n minus a number of elements for the part 1 only, and part 1 and part 2 minus part 1 is the difference which I have to give in the answer. Again, no worries, it's actually a very hard problem, because if you just go back and see, I have marked it as a hard plus, so no worries on that part. It is actually a hard problem, but we will still see everything from scratch. And if you get get something out of your head, just stop the video, go reverse it and just see it, because properly I have just explained everything in this. Now one thing you will say, Aryan, okay, that's great, I will simply make this, but on paper it looks very easy to make. How in real life I will be making that? Simply, we will use bit manipulation. Whenever you have to generate these subsets, you just simply use mask. Now if you are not familiar with these concept, bit manipulation, so we have an entire playlist in which in the beginning portion we discuss the main operations of bit manipulations, and then in the end we have many tricky problems and also super amazing problems for you to grab the entire bit manipulation, XOR, or entire masking. All that stuff will be covered in this video, this playlist. Just write bit manipulation by Aryan Mittal, you'll get the video, get the playlist itself. But for a quick walk through how a bit manipulation works is that if you have numbers, if I have an array, let's say array of size 4, or let's say array of size 3. Now if I have elements -2, 1, 4 and 1, now I want to grab, let's say, this element and this element, because a subset says I will try for all the possibilities. So I'll simply try to make a mask, which means earlier my mask is a 0, then my mask is a 1, then my mask is a 1 0. Now 1 0 is value 2, so I'll take at 0 value, 1 value, 2 value, 3 value, 4 value, 5 value. Now 3 value is 1 1, 4 value is 1 0 0. Now this 1 0 0 represents that I will take my this element, I'll not take this. Now this 1 1 represents I'll not take this, I'll take this. So this is why by this I can generate all the possible subsets for a specific array of size n. So this again, how far I will go? I will simply go saying, okay, my array size is, let's say, n. So I'll go on and say 2 raised to the power n minus 1 will give me the value. So 2 raised to the power 3 is nothing but 8, minus 1 will be a 7. So 7 can be represented as a 1 1 1. So it will cover all the possibilities for this subset. I'll do the same thing, that initially my n is nothing but entire array size. Again, remember, it's a big n, it's a big n. Then I'll have some variables. I'll show you the significance of those variables, but right now, if you remember, I'll take the entire sum of the array, because in the very beginning I told you that if my array is entirely of size n, I'll partition that, okay, and say that it is, let's say, part 1 sum. Again, it is part 1 sum, it is part 2 sum. I know part 1 sum plus part 2 sum is my target sum. Now this target sum is nothing but this specific sum. It is the input itself, and ultimately the problem is saying that part 2 sum minus part 2 sum and minus part 1 sum. This should be as minimum as possible. And if I just replace my part 2 sum with sum minus part 1 sum, so I'll just replace the exact same thing. So I'll get a sum minus 2 into part 1 sum. So this represents that I would be needing this part 1 sum if I want to only work on my part 1 sum. So I would be needing this sum to only work on my part 1 sum. I'll not touch my part 2 sum. No worries, it can be confusing in the very beginning. What is part 2 sum? What is sum? Sum is nothing but the entire sum of the array of length n. Part 1 is, I am saying, the final answer, which is the first array I will be making, and that array is a subset of elements of these n elements, and that part 1 sum will have a small n number of elements. It will also have a small n number of elements. To make this element, to make this specific array part 1 sum, I know, okay, I'll just simply try to build this part 1 sum. That's it. I'll not even touch or look at my part 2 sum. So I removed from the entire picture itself, so that I'll only work on my part 1 sum, which is this specific array. Again, when I say this specific array, first array, I mean first array, which means the part 1 sum array. It can be built out of some elements from left and some elements from the right. And some elements, when I say some elements, can be from, again, left portion is this entire portion and right portion is this entire portion, right portion. So some elements from this left and some elements from this right, as I showed you earlier also. Because this entire thing, this is the only thing which can make you confusing, and that's I'm just actually stressing it more. Now coming on back, that how to actually generate all these subsets, I'll simply use the entire masking technique. I will generate my left and right vector of vectors. Now this vector represents, okay, for a size of 0 1 2 3 4, what are all the sums possible for that specific size, as we saw. Okay, for that specific size, what are all the sums possible? For the specific size, what are all the sums possible? The same way I am doing here. For left and right, I'll simply go and build. Now I'll simply go again. You remember that, okay, your left and right both will be of size small n. So you will be generating 2 raised to the power n subsets for the left part, 2 raised to the power n subsets for the right part. So the same way, I'll generate my 2 raised to the power n subsets, right? And while I'm generating this specific mask, mask will generate all the possible subsets for you. But when I'm generating specific mask, I will populate my both left and right answer parallelly, so that I don't have to write the for loop again and again. Which means, one way is you make the all these subsets of the left, and then you again make all these subsets of the right. That is one way. But I know the same mask I will have to write, so it is the reason you will see I'll populate both of them parallelly. Have a quick look. Firstly, this mask will help me the same way I actually build this mask. This mask, let's say this mask is this. It helps me. This is the mask. This helps me to say that I should not take this value. I should take this value, and by default all the other values are 0. So I should also not take this value. This is how my mask help us to actually build my answer. So I'll go on and iterate on all the elements. Now whatsoever my mask says, okay, mask says that ith element, mask says the ith element is actually good to take. Then again, good to take, which means the and value is a non-zero value. It is good to take. If it is good to take, simply increase the size, because you have taken one element and also add in your answer. L is the left sum, because if you remembered, size I will increase, size I'll say okay I have taken two elements, but I want the sum of those two elements, sum minus 1, sum 1, sum 2, I want a sum also. So this L represents the sum of those left elements which I'm taking right now. And the same way for this specific size from the right portion, again this is the right portion I am taking, this is the right portion I am taking from the right portion. As you saw, I am just making the answer for both left and right parallelly. For the right portion I am taking this R as the sum. Now when I have tried for all the elements and using this mask, whatsoever size I have got for that specific size, whatsoever left sum and right sum I have got, I simply populate that in my vector. So left vector for this specific size, I have got this as one of the sums, and I'll try for all of the masks possible. And the same way for this right size, for this right array, right size, I'll push back this right sum. This is how I'll simply build this. I'll simply build my this right and my left vectors, right, vector vectors. Now when this portion is done, still there's one thing remaining. If you remembered, I will need to have a part 1 sum. If you remember the entire thing which I told you, ultimately my aim is sum minus 2 into part 1 sum, 2 into part 1 sum. I'll just give you a very quick brief overview of what this part 1 sum means. Again, if you know it, skip it. So this was our entire array, right? I bifurcated this array into two portions, left and right, left and right. Now I am saying my ultimate answer was bifurcating this array into part 1 sum and part 2 sum. Part 1 sum I'll say as a short form was P1s, and this was the part 2 sum. This was the part 2 sum, which is P2s. Now I am saying, as you saw, that I will again my total answer is I have to minimize my P2s minus P1s. The difference between those two, I have to minimize that. This is the absolute value, I have to minimize that. And I can simply represent, and I know that P1s plus P2s is nothing but the total sum, which is the sum variable which I have taken. So I can simply say that my P2s, which is a part 2 sum, I can simply say as it will be for sure sum minus part 1 sum. This is my answer. So I'll simply represent my answer by replacing my part 2 sum as sum minus part 1 sum. Minus part 1 sum will be the exact same value. Now it will become my sum minus 2 into part 1 sum. When this is the final value which I have to, which means I will try that my part 1 sum should be as close as to sum by 2. My part 1 sum should be as close as to sum by 2. That is my ultimate aim. Now, which means I will have to try on for all the possibilities for my part 1 sum. Now forget this part 2 sum for now. Now to generate all the possibilities of part 2 sum, as you remembered, I have generated all these subsets from the left and right. I know 2 to the power n will be from here, 2 to the power n will be from here, all the subsets. I will say that to make this part 1 sum, some elements I will take in from the left subset, which means let's say left is for size of n. This right is for size of n. I will take a number of elements from the left. So I'll take a number of elements. So it is a reason I will use left of a. A is a size, and thus I know the remaining elements of size, because I know the part 1 sum will have a size of n. So remaining element I will take from the right side, but remaining, which means how much, n minus a number of elements I'll take in from the right side. And thus I can know that okay, part 1, this left of a I have generated. If you remembered, I've generated all these subsets for all the sizes possible from the left side. So this left of a, I can try for all the possibilities, that what all sums can be possible. Same way, right of n minus a, what all sums can be possible. And with this sum, let's name it as a big A as a possible sum value, big B as a possible sum value. Now this big A plus big B will be the part 1 sum. Big A plus big B will be the part 1 sum, and this I will replace in here, which is this specific part 1 sum, which is this value, sum minus 2 into A plus B. And that is how I'm going to minimize my answer difference. Now coming on back, again I'll not repeat this now. So coming on back, we had just known one thing, that I have this entire value. I'll take some elements for the part one sum. For the part one sum, I'll take some elements from left, some elements from right to build my part one sum. Now to build my for the small example, to build my part one sum, I can have 0 elements from the left, n elements, which means 3 elements from the right, 1 from the left, 2 from the right, 2 from the left, 1 from the right, or 3 from the left, 0 from the right. All the possibilities taken. Correct, all the possibilities taken. So I'll try for all the possibilities, and that is how I can simply get the answer. So I just know that I will have the part one sum. Again, when I say I will take elements, so the part one sum will have a plus, okay, if I just say from the left portion I have grabbed the sum as a, from the right portion I grab the sum as b, so the total sum will be a plus b for the part one sum. So if you remember the same problem, the exact same approach which I taken, total minus part one sum, total part two sum is nothing but total minus part one sum. So I'll represent the same thing, total minus 2 into part one sum. So total minus 2 into part one sum should be more than equal to 0 because the absolute value. Difference is the absolute value. So my answer will become that total into 2 into a plus b should be more than equal to 0. Again, just a quick change which I did earlier. I took a as the number of elements, but here I'm taking a as the sum of those number of elements from the left side, b as the sum of those number of elements from the right side. So this a plus b is the sum of the left part of the part one sum. So ultimately my aim is I'll try for all the possible sums from the left, which is the a, and I will try to find the closest b possible such that b is the specific value. Right, as you remembered also in the very beginning, in the middle, I told you that my sum should be as close to as total by 2. Same way, I will try for all the possibilities of a, and my sum and this, okay, when I try for the possibility of a, let's say a is something, let's say a is 5. So when I say a, I mean the sum of the left part is 5. So when I have tried for this specific sum, I'll simply go and check, okay, if b, what is the value of b? Now if I choose a way, I'll try for all the possibilities, but for one specific a, I'll get this specific value of b, right? When I have fixed a, let's say a is fixed to 5, so I'll get total sum is fixed. This 2 into 5, a I have tried for 5, so I'll get a value of b. This value of b should be whatsoever value of b I have got. Again, value of b, if you have remembered, will be actually found in the right array which I have built. In that I will try to find the value which is as close to sum minus 2 into a by 2. We'll see by example this thing also. Now let's look at with example that how we'll solve it. Firstly, if you remembered, we simply made this left and we made this right. 2 into 2 to the power 3 elements, 2 to the power 3, 2 to the power 3 number of subsets, 2 to the power 3 number of subsets. Now when this portion is built, now exactly simple, that we are only concerned about the part one sum. Remember this fact, because ultimately I know that my answer will be part two sum minus part one sum, which is nothing but saying my sum minus 2 into part one sum is my actual answer. So I'm only concerned about part one sum. I'll not even look at my part two sum. Now to build my part one sum, I told you I can have multiple possibilities, either no element from the left, 1 element from the left, 2 element, 3 element, n minus 1 element, or n elements. This is for the part one sum. I'll just take these number of elements from the right, from the left, and for sure the remaining number of elements I will take for sure from the right, which means I know my part one sum will for sure have n elements. So if I've taken my 1 element from the left, so for sure n minus 1 element I'll take from the right. And same way, if I've taken 0 elements from the left, so for sure remaining n elements from the right. Now one thing, okay, you have tried for, let's say you have taken no elements from the left and you have taken all the n elements from the right for the part one sum, so okay, the possibility again, this possibility can be my sum, it is fixed, it can be 2 into part one sum. So for sure you can take my this right value, my part one sum will be my this right value. So part one sum can be my right of n. Again, if you remembered, my right of n is the size, and 0 indicates the first index value. And if you remembered very carefully, for the size of 0 and the size of n, I will only have just one element. For size of 0, I will only have my 0. For the size of n, I will only have my one element, which is 1. because it is the size of all the elements. All elements will give me one size, so I will have only one element. And the same way, my right of size of 0 will have only one element, and the same way my right of size of n will have only also one element. So it's the reason this 0 indicates the first element, and I will have only one element. If I just put a 1, I'll get an out of index error, which is for sure obvious. And the same way, if I take the n elements from the left side, I'll take my part 1 sum as left of n0. N is the size because I've taken left n elements from the left side, and 0 is the first element. So this is the cases which I have covered. But again, I also showed you I have also multiple cases. But right now, if you remember, I have to minimize my answer, which is a difference. Difference is sum minus 2 into part 1 sum. Part 1 sum either can be my left into left n0 or a right n0 for these two cases. You can consider them as edge cases, although you can handle them in the main case also, but right now consider them as edge cases. So right now you have tried to minimize the result, which is for sure your aim. But let's come on to the main cases. That okay, so far I have seen this, but I will have to go and find my part 1 sum. Now for the part 1 sum, I'll just try for all the possibilities. For the part 1 sum, I'll take one element from the left and remaining elements, which is n minus 1 elements from the right. So left size, this specific size is saying it is a left size, which means I took one element from the left and then I took n minus 1 elements from the right. N minus 1 elements from the right. So I'll just say size is nothing but the left size, R size is nothing but the right size. And the same way, let's say to build my part 1 sum, I am taking two elements from my left and remaining elements, which is n minus 2 elements from my right. So this is my size, this is my R size. Now, if you remembered from the algorithm, from the approach which you saw above, I will try for all the possibilities of A. So this is the size. I know that left of size, I will have many values of A because left of size is a vector. It is a vector. It can have many A's, like it can have many A's. So I'll try on for all the possibilities of my A's. Now for one such A, let's take one such A. For one such A, I will try to find the value of B. Now, as you saw above, my B will be sum minus 2 into A by 2. Again, take a pen and paper, dry run, because this sheet is very small. You can only see this portion, but you can only relate when entire this thing is visible, entire formula is visible, and entire dry run where it is gone, entire this thing is visible. Only then you will be able to understand. So take a pen and paper or take a screenshot and then work on this algorithm or work on this approach. Now coming on back, as I showed you, my B I will find out and say it will be sum minus 2 into A by 2 from the above formula which we have found out. Now this B, again, this B cannot be exactly matching. Now this B, if you have found out, this B I can only grab in from the right, because see, this A I have grabbed from the left of size. This B I could have grabbed from the right of this right size, which is RSZ. But I know okay, this value is the ideal value for me. So in this specific vector, again, this is a vector. If you remember, this is also a vector. This is also a vector, or basically an array. You can say anything. This is also a vector. So in this vector, this value should be as close, which means again, this is the ideal value. This is the ideal value. This is the ideal value which will give me n by 2 as sum. This is the ideal value which will give me n by 2 as sum. But I just want, okay, I can't be getting actual ideal value, so I'll just say, okay, this is the ideal value. Please go and try to search in your the array which you have made, right array of size sum, because sorry, right vector of size RSZ. You have these sums, all the possible sums as possible. So please find the closest sum to an ideal sum, which is sum minus 2 into A by 2. Find the closest sum which is equal to my ideal sum, and that closest sum I will name it as a B. Now to search for something in a vector, you can simply apply a binary search. But for that binary search to be applicable, this entire thing should be sorted. So what I will do is, I will go on to all the possible sizes, which means all the possible sizes, and I'll simply sort this vector for them. And I'll sort this for all the vectors. All the possible sizes. I'll sort it for the right, only for the right, because I'll go and try for all the possible A values A values but for one A value, I will try to find the ideal B value, and then ideal B value I'll try to search in this right of size. Okay, when this entire thing is done, I know I will have tried for the closest B possible value of B, and the closest possible value of B can be simply by a binary search. But when you apply a binary search, you can apply a lower bound or upper bound. But lower bound is giving me, okay, lower bound says if I'm trying to search for ideal value, let's say I, so I'll just, if I do a lower bound, so I will be pointing to a equal or a higher value, but upper bound says just a higher value. So for sure, I would need the closest value possible. So I will just be pointing to a equal or a higher value, because equal value is the closest value possible, right? So I'll just do a lower bound so that I'll point it to a equal or a higher value. If value equal is available, simply point to equal value. If not, then higher value. But then I'll point to a simple higher value. But you always remember that even if you point to a equal or higher value, there is a high possibilities that the next previous value would have been a closer value to my B. For example, if I have an array, let's say 4, 5, 9 and 4, 5, 9 and 10, and if I'm trying to search for a 6, so my lower bound will point me to a, because equal value is not there, higher value is 9, so my lower bound will be pointing to my 9. So if I go and find the difference, 9 minus 6 is a 3, but I should also try for a previous value, because it can also be close, right? Because you can see my 6 will lie somewhere here, so it can be closer to my 5 also. So if this is my current iterator, I'll try also for my minus iterator, which means just a previous iterator, which is a 5. And you can see right now also that 6 minus 5 is actually 1, which is smaller than 9 minus 6. So one thing is, I for sure that I will use a lower bound. Okay, after using a lower bound, I will be pointing to this specific iterator, but then I have to reduce my iterator and then try for that also as a possible value. So again, to find, okay, for an iterator is ITR, to find the value of that ITR, it is star ITR. Just, okay, what's the corresponding value to that iterator? That's the star ITR. And same way, go on to the previous iterator and find a specific value. These are the possibilities of my B, and I'll try for both the possibilities of my B. And again, when I try to both the possibilities of my B, if you remember, my result which I want to minimize will be nothing but sum minus 2 into part 1 sum, and part 1 sum is built out of A plus B, and B is the possible value of B, which is I have two possible closest values of B, which is close to my ideal value. Ideal value is this value. It is close to my ideal value, which is nothing but my star into minus ITR and also star of ITR. And that's how I can simply solve it. Have a quick glance on the code. The code for this portion will look like that. I'll try to do a lower, like simply binary search in my vector v. It is nothing but a vector which I showed you there itself. This is a vector, writes this portion, right? This is a vector v. For that right of our size, this is a vector v which I have found. Now this vector, I'll do a binary search. In that, if it is not equal to end, then I can simply try for a possible values of star ITR, and then if it is not equal to beginning, then I'll do a minus ITR, and then I can simply go and try for that specific minus ITR also. So with this, I'll try for both the possibilities of my B sum, and again my part 1 sum is nothing but A plus B, and my total part and my total difference will be nothing but sum minus 2 into part 1 sum, sum minus 2, and that is what I have to minimize. So it is the result which I will be minimizing. Now this is the entire code. Again, I'll just quickly walk you through the entire code all together also, but it will be more or less same. But make sure, if you have not understood this, it's a very hard problem, and also please take a pen and paper, because no other video in YouTube will actually teach you in just one page. I cannot show you everything like this. It's a mess up, because it's actually a very hard problem. Now coming back to the code, complete code, exactly same. First, in the very case, we just found the total sum, which is a sum variable for us. Then we went on and tried to build all these subsets of size small n and small n. So again, for small n, when I say, I mean the left. For small n, I say I mean the right. So here I tried to build all the subsets of my left and right, and when I say subsets, I build for every possible sizes. I grabbed on what are the all possible sums corresponding to that specific size, because I know that will be useful for me. Now when that entire thing is done, I know one thing for sure, I will be using my A in the left, iterate on all the possible sums of that left, size, and for that I need to do a binary search on my right. So I went on to my all the possible rights. I did a sorting on the right so that I can do a binary search on that right. Now I will now go on to my left, because I know my A is nothing but, okay, this is nothing but all the possible sizes. Now left of that specific size is a vector, and I know I have to iterate on all the possible values in this vector because it is a value for me. So as you can see, I just went on and got the A value from this specific vector. Now when I have got this value, I will try to find this B. This B is right now saying this is the ideal value which I should be achieving, which is sum minus 2 into A by 2. And for sure the remaining size, because if I've taken size from the left, then from the right I can only take n minus size, because I know this is the operation only for the part 1 sum. For the part 1 sum, it can be of size n itself, which is small n, and that is the reason I will have n minus size. Now when this entire portion is done, I'll simply go and say, okay, vector v is the vector which I showed you right here. This is the vector v, right? This is the vector v for the specific right of RSZ, right size. Now I will simply do a binary search of the specific ideal value on this vector b and find the iterator. Simply lower bound for this vector and searching for the value b, which is the ideal value of my b. But there can be a chance that the high, which means lower bound, may point to end. So if it is not pointing to end, then I can try on and say, okay, this is the current value of b, which I could have found, and the part 1 sum will be a plus b, and the difference will be sum minus 2 into part 1 sum. And the same way, if my iterator is not pointing to the beginning, so I can just decrease my iterator, which means minus itr, and then I can just try to check, okay, for that specific value, this is the new expected b, and a plus b is the part 1 sum. Sum minus 2 into a plus b will be my difference which I could have found. And that's how I'll try for both the possibilities, left, which means lower bound, and just before that lower bound, and with that I can simply find the answer by trying on for all the possibilities and minimizing my result, and that's how I can simply get my result. Now the complexity will be nothing but 2 raised to the power n. Now this n is the small n. Remember, it is not the big N. It is if the input array size is big N, which was 30 in our case, then it is a small n, which is 15, and the log 2 raised to the power n is nothing but binary searching on the right portion which we have. And for sure the space will be O of 2 raised to the power n, because you are actually storing, you are using a vector, right? Vector of left and right. So that left will show, okay, for that left size, what all sums I have? Nothing but all the possible subsets I will be storing as a vector, and that's how will be my space and time. Again, that's a very hard problem. In this you learn everything. You learned DP, you learned meet in the middle, you learned bit manipulations, you learned binary search. That is the reason why this problem is super hard. Again, this meet in the middle is a very tricky problem used in competitive programming, not asked in general interviews, but you see it has been asked by Uber, Google, Adobe, Salesforce, Samsung, Bloomberg, Microsoft, Amazon, PhonePe, Apple, Infosys. I don't think Infosys can ask this, but yeah, like lately Infosys have been asking this. God knows what they're planning to do, but yeah, that's how it is. Cool. Thanks for watching. See you goodbye. Again, if you didn't understand this, there's a high chance you would not, because it's a very hard problem and you might have not heard about this, and we are studying everything: binary search, bit manipulations, meet in the middle. Please go and take the notes parallelly with me. I will not give you the notes which I have made, because I know, okay, for sure I have this exact same notes. I always keep the notes with me, because I feel like it's actually good. I have the proper, without even writing, but I will not give, because then everyone just binge watch stuff. They just don't write by themselves. Unless you don't write by yourself, you will never ever learn. So yeah, thank you for watching. See you, goodbye, take care, bye bye.